Thank you for having us to present our solution to the request to design a control system for this important nuclear reactor that's deployable in emergencies. We realize that the problem is significant and that even short outages in electricity affect the loss of life and the overcoming natural disasters. For instance, here we have a hospital in New York that had to evacuate after Hurricane Sandy because they lost power after a period of time. One of 4 hospitals, actually, so this is an important problem. We've used sound engineering practices, including proven process control techniques, to develop a reliable and good system to approach this problem, and we've come up with 2 possible solutions that we'll present to you now.
So the first solution, we call it nuclear predictive, and so basically it's a nuclear reactor coupled with a gas generator, and this is kind of my baby. I tried to make sure this one worked right. And so what we did was we had a 20 megawatt gas generator, and then we used a nuclear. So this is a 25 megawatt generator. It's $17.5 million, but it fits on the back of a semi. And so the key here was, this is our demand difference with the megawatt difference. So sorry about that.
Just keep going, that's fine.
This is our demand difference for the nuclear with the natural gas. And so one important thing we did was, on the 24 hours we could get it to look really good, but when we extended it out to like 3 or 4 days, you start having differences that would start adding, and then you start seeing huge fluctuations in supply. And so the way we took care of this is we made a stair function to take care of the nuclear. So this is the nuclear stair function. So every 24 hours the nuclear will ramp up to 90, and then it'll go down to 60, and then it'll ramp up to 90, and then go down to 60 to follow the daily demand. And then this is the natural gas generator over the same time span. And so what's interesting is we zoomed in and measured and found out, so every 24 hours the gas generator only has to run for 6 hours, and it has an average output of only 6 megawatts. So for a month you'd only need to use about 4,500 cubic feet of natural gas. And so I thought that was really good. We can mainly use the nuclear, but then the natural gas would kick on in the large spikes.
Okay, now how do we get it to go to the next slide? There we go. So our other option, it has the same nuclear power generator, but instead of gas it uses 7.5 megawatts of fuel cells, which we use to replace the batteries. And it has the huge advantage of being self-sustainable. Because it regenerates its own fuel, it will keep going for years without outside help. And because it's a battery, it responds to power changes virtually instantaneously. And you can see from the chart, those spikes are very, very thin. They're almost instant. Because with 7.5 megawatts of battery, which in the case of a power spike, the energy that was charging the battery will reverse and go to the grid, and then the battery itself will go to the grid. So it can spike up 15 megawatts. Conversely, it can spike down 15 megawatts if we have a drop in energy. So we have a range of 30 megawatts of energy that is virtually instantaneously available from only 7.5 megawatts of fuel cell. The disadvantage is that they only last for about 5 years, and they cost about twice as much as the generator that Scott mentioned. So the Navy's never going to go for it right now. The capital cost is just too high. Maybe in 20 years when technology improves, when they're more than 40% efficient, then they could be a very real and very elegant solution. But right now it's just more cost effective to use natural gas, which is very low cost right now. So that's the one we recommend for the time being.
Yeah, and then if you have any questions.